Hi. Hi, I'm going to race this puck against this solid rubber ball down this ramp. Now they're both exactly the same material. The difference here is in the geometry. Look at the way the weight is distributed around the puck. It's shaped like a disc as opposed to a ball which is shaped like a solid sphere. 3, 2, 1. And as you can see, the ball won. And I'm about to show you why that ball is going to win every single time. Rotational kinetic energy is proportional to inertia. And inertia is how a mass is distributed around an axis of rotation. Now, once you learn integral calculus, you'll be able to understand a more precise definition and be able to calculate it, but this will suffice for now. So you can think of it, imagine you're jumping and turning. So if you were to jump and turn, you could have high inertia if you were to spread your arms out wide. And you could also have lower inertia if you were to pull your arms in. And that explains why if you jump and spin with your arms out wide and then pull your arms in, you will, in the air, spin faster. And that has to do with conservation of rotational energy and conservation of angular momentum. And how that's related to your inertia. Your inertia is how your mass is spread out around the center of rotation. The inertia for a puck, or well, the geometric shape of cylinder, inertia is half mr squared, where m is the mass and r is its radius. The inertia for a solid sphere or a ball is 2/5 mr squared. So as you can see, a cylinder, given say a similar mass and similar size, a cylinder is going to have a higher moment of inertia than a sphere. And if you were to take a solid quantity of rubber and form it into a puck, it's going to have a greater radius. And even for the given radius, it's going to have a higher moment of inertia than a solid rubber ball will. Now, that's proportional to its kinetic energy. So what that means is a spinning ball will hold less rotational kinetic energy than a rolling puck. So now let's consider this problem you just saw in the video. A puck with a mass, and I looked this up for a hockey puck, it's got a mass of 160 grams and a diameter of 7.6 centimeters. And we also have a ball with a mass of 140 grams, so comparable mass, and its diameter is 4.5 centimeters. Both of them roll down a 1.3 meter plank, and that plank is elevated at 0.3 meters at one end. We're going to calculate the theoretical travel time, so how long we would expect for them to take to go down the ramp to see if theoretically that ball should win, as we just saw in the video. And then we're going to try and determine if a toy car would beat the ball rolling down a ramp. Okay, so a cylinder has a moment of inertia of 1/2 mr squared, and the ball has an inertia of 2/5 mr squared. And what's happening in this situation, in both cases, we have an elevated mass, a raised mass, and it's put on a ramp and it's allowed to roll its way down the ramp. So what's happening is at the very top, all of the energy is gravitational. When it makes its way down, all of the energy is kinetic. Now that kinetic energy is the energy associated with the mass that is moving. However, imagine a rolling body. A rolling body is moving not just in a line, but it's also spinning. So we have to account for both of those forms of motion when we keep track of all of the energy in the system. So for a rolling puck, we have kinetic energy, and the kinetic energy is 1/2 mv squared. That's the translational kinetic energy, plus 1/2 I omega squared, where I is its moment of inertia and omega is the angular velocity. So that's how fast it's rotating in radians per second as an angle. Now, when we're looking at the puck, we've got half mv squared plus half I, and remember I, the moment of inertia for the puck, is half mr squared. Times omega squared. Now, what is omega squared? Omega squared is actually v squared over r squared. Now, let me call this digress. Let me quickly explain why omega squared is v squared over r squared. So consider a rolling ball or a rolling puck. As it moves to a point from where this is on the ground to where this is on the ground, it's gone a distance, s. And if it has radius r, then the angle of rotation is angle theta. And if we're measuring this in radians, theta is the arc length over the radius. So that angle is equal to how far this body has rolled in a line divided by its radius. Now, if we were to look at the rate of change with respect to time, so the rate of change with which that is moving with respect to time is its speed, then the rate of change at with which that angle is changing with respect to time, that's the angular velocity omega, is the linear speed divided by the radius. Now, if you want to make this make sense to you, imagine a roll of duct tape and a pencil, and you're to roll them both along at the same linear speed, so they're both going the same distance in the same amount of time. Which one's going to have a faster spin? Which one's going to spin at a higher rate, turn around more times per second? The pencil is, because it's got a much smaller radius than that roll of duct tape. So for them to have the same velocity with a lower radius, you would have a higher angular speed. And they're related in this way. So when I'm looking at the rotational kinetic energy, that's the half I omega squared that you see here. I is the moment of inertia, and omega is v over r. So omega, your angular velocity, is your linear velocity divided by your radius. So if we keep going here, we've got half mv squared. Now remember, this is all for the cylinder. This is for the puck. Half times a half is a quarter, so that's 1/4. And I've got m r squared v squared over r squared. So those r squareds, they cancel one another out because they show up at the top and the bottom of this term. So that becomes 1/2 mv squared. So that makes the total kinetic energy of the puck equal to 3/4 mv squared. That's the total kinetic energy of the puck. So let us now consider the ball. So for the ball, its kinetic energy is its linear kinetic energy, which is half mv squared, plus its rotational kinetic energy, so that's half I omega squared. So notice how the rotational kinetic energy is proportional to inertia and proportional to the square of the angular velocity. So that's half mv squared. And remember, for a ball, its moment of inertia is 2/5 mr squared. So that's 2/5 mr squared. And omega squared is v squared over r squared. That's an r there. So again, we can cancel those r squared values. And what that leaves us with is 1/2 mv squared plus 2/10 mv squared. So we have 5/10 plus 2 more tenths is 7/10 mv squared. That is the kinetic energy of a rolling ball. And again, that's if the ball is solid. So when we race a puck and a ball down a ramp, and all the gravitational potential energy gets turned into kinetic energy for the puck. So let's look at the puck and the ball. For the puck, the gravitational potential energy was mgh, and it all gets turned into kinetic energy, which was 3/4 mv squared. For the ball, the gravitational potential energy was mgh, and that all gets turned into kinetic energy, which was 7/10 mv squared. Now I know I gave you the mass of the puck, the mass of the ball, the radius of the puck, the radius of the ball. Have you noticed that the radius cancels out? So how the gravitational potential energy gets turned into linear kinetic energy is independent of the radius for both the puck and for the ball. It depends on the geometry. We have different coefficients here depending on if it's a cylinder or if it's a solid sphere, but it's independent of the radius. What I want you to notice now is it's also independent of the mass. See, the mass cancels here and the mass cancels there. That should come as no surprise. Both of these are accelerating due to gravity, and one of the things you learned very early on in physics is if you drop any two masses, and their masses can be different from one another, they're both going to have the same acceleration due to gravity. And because we're rolling this down a ramp, it's only gravity providing the acceleration, so we should expect it to be independent of the mass. So for the puck, we're going to find the final velocity is going to be, we've got gh, and we'll multiply both sides by 4, divide by 3. That's going to give us v squared. So that means that v is going to be the square root of all this. And for the ball, same thing. We're going to have 10 gh over 7. That would give us v squared. And if we take its square root, that's going to give us v. So that means the final velocity of the puck is the square root of 4 times 9.8 times 0.3 was our height, all divided by 3. And for the ball, the final speed is the square root of 10 times 9.8 times our height of 0.3, all divided by 7. So we'll have a final velocity of 1.9799. And so that was for the puck. And for the ball, we're going to have a final velocity of 10 times 9.8 times 0.3 divided by 7's square root 2.05. So as you can see, the ball is going to go slightly faster at the very end than the puck, and that's what we observed with our experiment. Now keep in mind, this is the final velocity. And so that's actually V2. That's the final velocity of each of these. That's when all the gravitational potential energy got turned into kinetic energy. The initial velocity was 0 for each of them. So the average velocity is the average between the initial and the final velocity. Now that does not always work, but it certainly works in the case of gravity near the surface of the Earth, because we have constant acceleration due to gravity. That's why this little shortcut here works. So we have an average velocity for the puck of 0.9899 meters per second, and an average velocity for the ball of 1.025 meters per second. So when we race them both that distance of 1.3 meters, our delta t is going to be our distance divided by our speed. And because this motion's in a straight line, I can divide by the velocity. So it is 1.3 over 0.9899 for the puck. And delta t is 1.3 divided by 1.025 for the ball. So it is 1.313 seconds for the puck, and it is 1.268 seconds for the ball. That's why you saw the ball win slightly by somewhere around 1/10 of a second. Okay, so let me recap this problem here. We are rolling both a puck and a ball down a plank. That plank has a length of 1.3 meters and was elevated at 0.3 meters. As the puck and the ball roll, the gravitational potential energy gets turned into kinetic energy. But that kinetic energy has two forms, because they're not just simply sliding. The two forms of kinetic energy are translational, that's moving in a line, and rotational, that's the spinning portion. The kinetic energy that they have depends on the inertia. Inertia is a property of the material that tells you how the mass is distributed around an axis that's rotating. For a cylinder that's rotating around its center, it's going to have a moment of inertia of 1/2 mr squared, whereas a sphere is going to have a moment of inertia of 2/5 mr squared. Now, upon learning integral calculus, you can look up a more precise definition of inertia, which has to do with looking at each individual particle of mass as a single point, and you look at its density, and you integrate, and you end up with these values for these particular shapes. Anyway, what it basically means is if you have your arms out, you have high inertia. If you tuck your arms in, you have low inertia. And you can observe that phenomenon yourself. Put your arms out wide, jump while spinning, and pull your arms in while you're in the air. You're going to notice your body accelerates. You're going to rotate faster. What's happening there is you're lowering your moment of inertia without changing the total amount of kinetic energy, because that energy is remaining constant while you're in the air. So in doing so, with a lower amount of inertia, you're going to need a higher velocity. That's why your body speeds up. So we've got our kinetic energy is our linear portion of kinetic energy. That's the half mv squared, plus the rotational portion of kinetic energy. That's the half inertia omega squared. And for the puck, or the cylinder, solid cylinder, we've got half mv squared plus half mr squared. That half mr squared is the inertia of the cylinder times v squared over r. V squared over r because omega is v over r. Your angular velocity is your linear velocity divided by radius when a body is rolling. Do a little bit of algebra to that, and the total kinetic energy for a puck or a cylinder is 3/4 mv squared. Apply the exact same process to a solid ball, but putting in a ball's moment of inertia of 2/5 mr squared, you end up with a kinetic energy of a ball is 7/10 mv squared. By turning all of the gravitational potential energy into kinetic for both the puck and the ball, canceling out all of our variables, plugging in the known values, we end up with a final velocity for the puck of 1.9799 meters per second, and for the ball it's slightly higher at 2.05 meters per second. That was the final velocity. That's when all of the gravitational potential energy got transformed into kinetic. So the average velocity is the initial velocity of 0 plus the final velocity divided by 2. We get to make that assumption because it's falling due to gravity, so it has constant acceleration. You don't get to do that unless you have constant acceleration. So going a distance of 1.3 meters, we divide by our velocities and end up with 1.3 or 1.27 seconds to roll down the ramp, explaining why the ball beat the puck just slightly. Now, what do you think is going to happen when we race the ball? So that ball won. So let's say we're to take a ball and let's race a toy car. So a toy car's got these really light wheels, and the bulk of the mass of the toy car is just simply going to move in a line. So almost all of the energy of the toy car is going to be linear translational kinetic energy. It's going to have some, but not much, rotational kinetic energy, because those wheels that it has have very light mass compared to the rest of the car. So what do you think is going to happen? We're now going to race the ball, which had won, against this racing car. Okay, go Sammy.